Our next speaker, or second speaker, is Andrei Krokhin. I'm not sure I pronounced your name correctly.
Yeah, that's fine. No worries.
Close enough. He's worked extensively on constraint satisfaction problems, CSPs, which are a generalized form of SAT, and that's of interest to 50 years of SAT workshop, of course. He's talking today on classifying the complexity of SAT and CSP. Are we there yet? So please go ahead.
Thank you, Sam. So let's start. Of course, I will start from where it all began, from Schaefer's paper, 1978, where he looked at generalized satisfiability problems. So they're just like SAT, but instead of clauses, you use relations, Boolean relations of specified arity. So if your gamma contains some relations, say R1 is a ternary relation, R2 is a binary relation, and so on, then an instance of SAT gamma looks like this. So you take some tuples of variables and apply your relations to them. And then the question is whether there is an assignment from the variables to 0 and 1 that satisfies phi, meaning that for every, say, the values of x, y, and z, this triple belongs to R1, and so on. So the special cases of SAT gamma are, of course, K-SAT problems, because clauses define relations. Horn K-SAT, the same. It's a special case of SAT gamma. K-lin, linear equations, modulo 2, with at most k variables. Well, they, of course, they define some relations, so you can use those to define your problem, and then what you have is the problem of solving systems of linear equations modulo 2. Now, what Schaefer did, he worked with gadgets. So he defined some relations from other relations by gadgets. So let's say that a relation R is expressible by a gadget over your given set gamma if there is an instance phi, which is drawn here, of SAT gamma, such that R can be obtained as follows. You look at all solutions to your instance. This is some relation, obviously, and then you choose some variables here and project out all the rest. So in this case, your phi would use 5 constraints, all using relations from gamma. It uses 9 variables, and then you look at all the solutions to phi, that's some relation, and then you project out all the variables except for x3, x5, and x7. So this is what it means to express something by a gadget. Of course, if you have your gamma and some R is expressible by a gadget over gamma, then you can add R to gamma without changing the complexity of SAT gamma, right? Simply because every occurrence of R can be replaced by this gadget in any instance, okay? So you can easily get rid of R, replace it by a gadget over gamma. And that was the key notion. So what Schaefer proved is that if you take any non-trivial gamma, non-trivial means that it's not true that every instance can be satisfied by simply assigning the same value to all variables. So that's what I call trivial. So if we have a non-trivial gamma, then exactly one of the following holds. Either SAT gamma is a sub-problem of one of the known tractable cases of SAT, such as 2-SAT, Horn SAT, its dual, or systems of linear equations modulo 2. And when I say sub-problem, more exactly, this means that every relation in gamma can be expressed by a gadget over the corresponding problem. So for 2-SAT, that would be every relation in gamma can be expressed as a conjunction of 2 clauses, possibly with some variables projected out. So this is one case. You are expressible by a gadget over some tractable case, then you're tractable. And the other case is when you can express 3-SAT by a gadget over gamma with additional constant relations. And then SAT gamma is NP complete. So This idea of expressing things by gadget is important. It will go throughout the talk, and we'll get back to it many times. Okay. Well, in particular, from this theorem, it follows that the following two problems are NP-complete. These are special cases of SAT gamma, and we will use them later. One is called 1 and 3 SAT, and that's when gamma contains the only relation, ternary relation, like this, R1 and 3. So that's 1 and 3 SAT. And the other problem is not all equal SAT. Again, it's a problem SAT gamma, where gamma contains a single ternary relation, are not all equal, which contains all triples of zeros and ones, except for all zeros and all ones. So these are standard now NP-complete problems that are used in many cases as a starting point for many reductions. We'll get back to these standard NP-complete problems later. So that was it. 1978. Question asked, question answered. That's it. End of story, right? Well, this is what it looked like back then. And then nothing much happened in the 80s. Well, some things happened in the parallel universe. Some considerations regarding graph homomorphisms. So if you have two graphs G and H, then what's a homomorphism from G to H? Well, this is simply a mapping from the vertices of G to the vertices of H that preserves the edges. If you have an edge in G, then the images must constitute an edge in the graph H. Notice that if your graph H is a k-clique, then this homomorphism or such homomorphism is simply a k-coloring of G. And this is why this generalization from coloring to homomorphisms is called the H-coloring problem. Given a graph G, is there a homomorphism from G to H? So of course, for k-coloring, it's been known for a while that the problem is NP-complete. It was known that for any bipartite graph, the problem essentially reduces to 2 SAT, so it would be a solvable polynomial time. And there were other separate cases for non-bipartite graphs H, where the problem was known to be NP-complete. So naturally, there was a question about the general picture. So what happens if H is any graph? And this question was raised by many researchers. And eventually, Helen Neshetril resolved this and proved that for any undirected graph H, the H-coloring problem is solvable polynomial time if H is bipartite or has a loop. Well, having a loop is a trivial case, of course. So, and in all other cases, it is NP-complete. Well, curiously, this famous paper doesn't even cite Schaefer's paper. So clearly, Helen Neshetril thought that they were doing something completely different, unrelated to Schaefer's work. Well, not that this turned out to be the case. Actually, of course, these problems are related. They are both special cases of the constraint satisfaction problem, and let me define this problem now. So I will fix a relational structure A, which is simply a finite set A, the domain of my structure, and a finite set of relations of various arities on the domain. Then an instance of the constraint satisfaction problem with this structure A looks like this. So again, we have some variables, and to some variables we apply the constraint R1, to some other variables we apply the constraint R2, and so on. And the question is the same as for generalized satisfiability. Is there an assignment from variables to the domain that satisfies this formula? Okay, it satisfies all constraints. So this problem was considered very, very actively in the artificial intelligence community. This is actually where this particular formulation came from. So that was, again, a different community that didn't know anything about Schaefer or Helen Neshetril. But the insight from Feder-Vardi and Jeavons independently in the mid-90s was that CSP can be considered as a homomorphism problem, that's providing a uniform framework for all that happened in AI or graphs or satisfiability. So how do we do it? How do we do this? So let's make a structure, a new relational structure. I call it I, for instance. Its base set will be variables. These are all the variables that appear in phi. The relation corresponding to R1 contains all the tuples of variables that are constrained by R1. The relation corresponding to R2, you can see that they're color-coded here, contains all the tuples of variables to which R2 is applied, and so on. And then satisfying assignments for the formula phi are precisely the homomorphisms from I to A. What's homomorphism from I to A? Well, it's a mapping from the domain of I, the variables, to the domain of A, which is this set A, which preserves all the relations, meaning that every tuple here is mapped into R1, every tuple here is mapped into R2, and so on. So CSP and the homomorphism problem for relational structures is the same thing. This is what Feder-Vardi and Jeavons observed. And then, of course, it's clear from this that generalized SAT and edge coloring are special cases of CSP. Now, it was this paper by Feder and Vardi, conference version 93, journal version 98, that really put the CSP on the map and made it known in all of the theoretical computer science community. So the main motivation for this paper was this motivation: find a largest natural subclass of NP that avoids intermediate problems. So we know from Ladner's theorem that if P is not equal to NP, then NP contains intermediate problems, neither polynomial time solvable nor NP complete. So what this question asks is this. So what is the natural class that avoids all these NP intermediate problems? And Feder and Vardi naturally used logic to define their class. So they defined this complexity class called MMSNP. So they took SNP. SNP is the strict NP. So you take NP and make a syntactic restriction of it called strict NP, which is contained in NP, but it is equal to NP up to polynomial time equivalence, which means that for every problem in NP, there is a polynomial time equivalent problem in strict NP. So in particular, if NP contains intermediate problems, then strict NP also contains intermediate problems. So Feder and Vardi took this SNP and considered three restrictions for it: monotone, monadic, and without inequalities. I'm not going to define what these restrictions mean. The point is this. So if you take SNP and apply not all three of these restrictions, but any two of them, then we still have that this class is equal to NP up to polynomial time equivalence. However, if we impose all three restrictions at once, then this is what we get, this class MMSNP. And what we can tell about it is that it contains all the CSPs. It strictly contains all CSPs, but these two classes are again equal up to polynomial time equivalence. Okay, so for every problem in MMSNP, there is a polynomial time equivalent CSP. Well, actually, in the original paper by Feder and Vardi, one of these reductions in the equivalence was randomized, and it was later de-randomized by Kuhn. So Feder and Vardi made this dichotomy conjecture, which says that each problem in this class, each CSP of A, is either solvable in polynomial time or NP complete. In other words, CSPs cannot have intermediate complexity in NP. And clearly, if we can prove this for CSP, it follows that MMSNP would also have a dichotomy, P versus NP complete. So this was the main motivation of Feder and Vardi, but this paper is famous for many reasons. And one of them is the richness of ideas and diversity of ideas in this paper. So I will just mention a few. So one idea was to introduce two general types of polynomial time algorithms that can be used for CSPs. One algorithm, well, it is known by many names, and it is the most natural algorithm you can invent for constraint satisfaction problems. It is based on local propagation, or its logical version called data log. Sometimes this is called the KL algorithm. And this is how it goes. You take your instance, and then you take two integers, k and l. So l should be greater than or equal to k. Okay. And then you introduce a constraint for each set of k variables in your instance. And this constraint initially allows all possible combinations of values. And then you repeatedly solve subinstances with L variables, one at a time. So once you solve such subinstance, you rule out some assignments of values to the variables. This is projected onto the relevant sets of k variables, and so we tighten the constraints on such sets. So this is kind of similar to maybe resolution to some extent, but the point is that we repeatedly tighten the constraints until the situation is stable. And then what can happen in the end is that we can rule out all possible assignments of values to some k tuple of variables, in which case, of course, the instance is refuted and we output no, and this no is, of course, a correct answer. If the procedure has stabilized, but we haven't refuted the instance, this means that the instance is now locally consistent. And in this case, we answer yes. Of course, this yes answer doesn't mean that the instance is satisfiable, right? This just means that it became locally consistent without refuting the instance. So for some CSPs, this actually is a solution procedure. For some CSPs, local consistency implies global consistency. For some, but not for all. So I will discuss this later again. And by the way, this local propagation algorithm can always use a pre-processing for any instance. You can take any instance and make it locally consistent in polynomial time. Again, I will use this later. So this was the first type of algorithm. The second type of algorithm was what they called subgroup problem, subgroup algorithms. So they thought that constraints would be, in this case, the cosets of the nth direct power of some group, subgroup G. And roughly, the algorithm goes like this. So you introduce, so you take your constraints in your instance into consideration one by one. So you add them one by one. You start with the first constraint, C1, then you add the second constraint, C2, and so on. And the algorithm processes those instances iteratively. And at each step, either the algorithm reports no solution, or it produces a representative for phi I, which is used in step I+1. So this is roughly how it goes. Let me briefly mention some other selected insights from this paper of Feder and Vardi. They observed that some closure properties seem to be somehow relevant to tractability of CSPs. They didn't make it very precise or took it very far. They just observed that there seems to be something going on in this direction. And also simulation by gadgets is somehow relevant. These properties, closure properties and simulation by gadgets, was something that was developed independently and more or less at the same time by the group of Jeavons and his co-authors. So their insights was like this. So if we want to use gadget reductions between CSPs, then actually we don't need explicit gadgets, right? So we need to know that they exist, right? If we know gadgets exist, we know we have reductions. And say Schaefer used very explicit reductions, very explicit gadgets in his reductions. But we don't actually need that. So they asked this question: is there a general theory of gadget reductions? can we reason about the existence of gadget reductions without building gadgets explicitly? And their key observation was that this is somehow related to things previously studied in algebra. So let me give this definition on an example. Say we have a graph H, and then an n-ary polymorphism of a graph H is simply a homomorphism from the nth power of H to itself. What is an automorphism of a graph? It's simply a mapping from actually homomorphism from the graph to itself, which is bijective. That's an automorphism. What's an endomorphism? Well, it's just a homomorphism from the graph to itself, not necessarily bijective, just a homomorphism. So this is somehow a continuation of this line, a generalization of endomorphism or automorphisms to multivariable functions. So all polymorphisms of H are denoted like this, and you can represent this pictorially. So if you have some n edges in H, you have an edge from A1 to B1, from A2 to B2, and so on, from AN to BN. And then you apply F to one side of the edges, you apply F to the other side of the edges, and you get, again, two elements in H, and there must be an edge between them. So this is what it means to have a polymorphism of a graph, and this extends in a natural way to, say, ternary relations, right? You just need to do it like this, and then here you would have. So you, if you take n triples in your ternary relation and then apply your f component-wise, the result must also be in the relation. So in this way, we can generalize this notion of a polymorphism to arbitrary n-ary relations and then to relational structures by simply saying that you must have a polymorphism of every relation present in your structure. So the meaning of this is that polymorphisms are higher dimensional symmetries. So if we view automorphisms as symmetries, then endomorphism also is symmetries that are not necessarily bijective. So polymorphisms are also symmetries, but higher dimensional ones. And it's very important because they carry important information about your structure, your graph, that is not contained in the automorphism group or endomorphism monoid. The key property of polymorphisms is that they compose, meaning that if you take two polymorphisms, say G of UV, and you have another ternary polymorphism F, and you compose them like this, so you form, say, a Fourier function like this, then this function would also be a polymorphism. So you can build polymorphisms, larger polymorphisms from smaller polymorphisms by using composition. So this is the key theorem that relates polymorphisms and gadget reductions. That was proved by Jeavons and his co-authors in 1997, roughly, building on some earlier developments in algebra by Bulatov-Zhuk, Kotov, Kaluzhnin, and Romov, and Geiger, independent works. So what this theorem says is that if you have two structures with the same domain, then the following things are equivalent. There is a gadget reduction from the first CSP to the second CSP, and the polymorphisms of the second CSP are also polymorphisms of the first CSP. So it goes the opposite way. The more polymorphisms, the easier the problem. So in particular, so this theorem says that the existence of gadget reductions is controlled by polymorphisms. Okay, and if you take the special case of this theorem, when actually pole A prime is equal to pole A, then this theorem says that CSP of A and CSP of A prime have gadget reductions going in both directions. Right, so if you want to reason about their computational complexity, then you don't have any reason to distinguish them, right? If they have the same polymorphisms, then they have the same complexity. So it makes sense to reason about the complexity of CSPs through polymorphisms, because then you can capture classes of equivalent problems at once. So this was the notion of gadget reduction, pretty much the same as used by Schaefer. And for this, you need that the structures have the same domain. In fact, this notion can be generalized to relations on different domains when A uses one domain and A prime uses a different domain. This is a sort of a generalization, but it's very natural. Again, this is what you would call gadgets still. And bringing it fast forward a little bit, this result by Bartol, Parshall, and Pinsker says that there is this more general gadget reduction from CSPA to CSPA prime, if and only if instead of containment of pole A prime in pole A, you have something called a minion homomorphism. So I won't explain what it is exactly, but you can think of it as containment on the abstract level. So that you can use it to talk about polymorphisms defined on different sets. So this is somehow similar to when you go from permutation groups to abstract groups, right? On permutation groups, you can talk about inclusion of one group in the other, but then for this you need that these permutation groups act on the same set, right? If you want to talk about a homomorphism from one group to the other, then they don't have to be on the same set. So this homomorphism, group homomorphism, is an abstract notion which is somehow more general than set-wise inclusion. So this is what's going on here. Again, the important point is that we know exactly when gadget reductions work. Now, let me discuss very briefly what we can call trivial symmetries, trivial polymorphisms, and non-trivial symmetries. So if we look at polymorphisms of any structure, this set of polymorphisms, then it always contains the set T of trivial polymorphisms. These are the n-ary operations of very simple form, like this. So it's an n-ary operation. It takes an n tuple and outputs the ith argument. So they're called projections, or sometimes they're called dictators in a different community. So very simple functions. They don't do anything. They just output the ith argument that they get. So why do I call such polymorphisms trivial? Because they are present everywhere. Every structure has them. So having such polymorphisms doesn't tell you anything at all, because every structure has them. But curiously, some structures have only such polymorphisms. So for example, if you look at 3-SAT, the corresponding structure that gives 3-SAT as a CSP, then it has only such polymorphisms, only trivial polymorphisms and nothing else. And this is a relatively easy exercise. You can do it on your own on a napkin in 5-15 minutes. And I'm not showing off. It's really very simple and elementary. All you need is the definition. That's it. So now, if we again go back to the previous slide and look at this condition, that pole A has some kind of homomorphism to this set of trivial functions, then this exists if and only if there is a gadget reduction going the other way from 3-SAT, which is the CSP corresponding to this, to CSP of A. So this happens if and only if, again, we have a gadget reduction from 3-SAT to our CSP. So in this case, of course, the CSP would be NP complete. So we can take this condition to mean that the symmetries of A, the polymorphisms of A, are trivial on the abstract level. So they're like projections. They don't have to be exactly that, but on the abstract level, they behave exactly the same way. So this is what I will call trivial. Right, there's a question in the chat. K set has only trivial polymorphisms. Yes, if K is at least 3. 2 set has non-trivial polymorphisms. For example, the ternary majority operation on the Boolean domain is a polymorphism of 2 set. But 3 set and all the other K sets have only trivial polymorphisms.
Can I ask a question also?
Yep.
A sub 3 sat there, that's a structure? I'm not sure what that is. On the
3 sat, you can, so you see, if you use the homomorphism view, then what you need is a relational structure that has a relation for every type of constraint that can appear in 3 sat.
Okay.
Right? 3 sat can have, 4 types of clauses, right? Involving no negation, 1 negation, 2 negations, 3 negations. So these are the 4 relations that you would have in this structure corresponding to 3 sat.
Thank you.
Okay. Good. So right now these are the trivial symmetries. So what makes symmetries non-trivial to prevent this condition, to prevent that we have a gadget reduction from 3 sat? Well, I will sort of hand way through this on an example. So this thing is a minion homomorphism, whatever it is. But what it does is that it preserves solutions to systems of equations. So what do I mean by that? So let's look at this and think of this as an equation where f is an unknown function. So f is an unknown function. It has n variables. And what we know about f is that if we identify all variables in f except for 1, right, then we get a binary function depending on x and y, and this function will be the same regardless of where this sole y is. Okay, so this is an equation where the variable is f, right? It's the unknown. So it's a system of equations which you want to solve in your set of functions, right? So if you either you have in your set of functions a function f satisfying this, or you don't. So this minion homomorphism preserves solutions to systems of equations, which means that if you have, if this system is solvable here, so if A has a polymorphism like this, then T would also contain a function that satisfies this system of equations. But this cannot be the case. Look at this. Can this system of equations be satisfied in projections? So the question is, can we find a projection P which we can substitute for f and get equalities everywhere? Now, if f is the projection, sorry, if P is the projection of the first variable, so let's look. Can the projection of the first variable be the solution? Well, then this would return y, and this would return x. So these would be different functions, right? This function is a binary function that always returns y, and this would be the binary function that always returns x. So they are different functions. Can f be the projection of the second variable? No, because we just look again at this y and say this x. So it's impossible. Well, you probably get how this goes. So f, if it's so what I'm trying to say is that there is no solution to this system of equations in projections. You cannot find a projection satisfying all these equations. And this means, in particular, that you don't have this minion homomorphism, so that 3 sat, there is no reduction, there is no gadget reduction from 3 sat to your CSP. So this is what it's about, right? Systems of equations satisfiable or not satisfiable in your symmetries. This is what determines how strong your symmetries are. Now let me move on and look at structural universal algebra, which is somehow the next step from what Jeavons did by bringing some kind of a universal algebra into the CSP business. So structural theory of universal algebras is an independent field. It's a very deep theory that was actively developed from 1950s with lots of very, very deep results. But it's not very widely known. It's not groups. It's considered generally more esoteric, despite the sheer strength of the results that were obtained in this theory. And somehow generally, this is considered by computer scientists as a deep dark wood. You don't want to go there unless you have a local guide. Or maybe even in this case, you don't want to go. So the general theory of gadget reductions is a simple thing. You can somehow intuitively understand what this means, right? One problem gadget reduces to another if and only if something happens. But this structural theory of universal algebras, that's really deep thing. So it was the connection between CSP and this theory was somehow made very explicit and clear in a series of papers by Bulatov, Jeavons, and myself. And in particular, there we observed that if your structure A, if your CSP has only trivial symmetries, then CSP isn't complete. And we made this conjecture, which was called the algebraic CSP dichotomy conjecture, that says that in all the other cases, which means if A has any non-trivial symmetries, then CSP of A is solvable in polynomial time. So this is a refinement of the Feder-Vardi conjecture because it specifies where the boundary is. And the boundary, well, it's very simple. Trivial symmetries means 3SAT reduces to your problem by gadgets. Non-trivial symmetries mean that there is some substructure in your problem which you can use to provide a polynomial time algorithm. Well, of course, that's hard. That's not easy. It's just some non-trivial symmetries. What does this mean? Maybe you can have some very weak non-trivial symmetries. This conjecture was actually confirmed in some important special cases by Bulatov. For example, for the case when A has a 3-element domain, or when all unary relations are available. And actually, there were very many mutually beneficial developments between CSP and universal algebra. In particular, a series of papers, for example, by Mackenzie and Marotti and Bulatov-Zhuk, prove that if you have some non-trivial symmetries that actually have very strong symmetries, there is some kind of algebraic dichotomy there. You don't have just moderately weak non-trivial symmetries. Either you have trivial symmetries or strong, which was excellent, of course. So there are two main algorithmic ideas for CSPs. One is just the same as Feder-Vardi, local propagation. So again, the no answer delivered by local propagation is always correct. The yes answer is not always correct, but for some CSPs, it is always correct. And the full description of when this works was given by Bulatov-Zhuk. The other idea evolved quite a bit from Feder and Vardi. So it's somehow similar, but more general. So again, you take your instance and you throw in constraints one by one. C1, then C1 and C2, then C1, C2 and C3, and so on. And then you iteratively compute a small poly-size generating set for these instances. So you start from C1, you get a generating set for just C1, just this one constraint. Then you have this generating set, you add C2, and from X1 and C2, you compute X2, a small generating set for these guys. Then you have X2 and you add C3 and you compute X3 from that. And so on. And then in the end, you have Xn, which is a small generating set for the solution set of the whole instance, which is either empty, in which case you have no solution, or it's not empty, in which case you have solutions. In fact, you have even some representation for the whole set of solutions. And again, there was a full characterization of when this algorithm works, because of course, not always you have such small generating sets. And when you do have them, you can actually compute them in polynomial time. So Ijak, Mackenzie, Marotti, Valeriot, and Willard fully characterized when this few subpowers algorithm works. And then all these eventually led to the resolution of the Feder-Vardi conjecture by Bulatov and Zhuk independently in 2017. So I will very briefly discuss the algorithms of Bulatov and Zhuk. They are very similar on a very, very high level, but all the details are different. So both algorithms heavily use some forms of local propagation, different forms. And in Bulatov's case, it's not even very local. Both algorithms are recursive, and they use a range of different rules for reducing instances or splitting instances in several parts. And then once you reduce your instance, you take it as the starting instance and start from that, you recurse. So the base cases for recursion roughly are the follows. Well, if all the domains of all variables are reduced to singletons, then you just have a solution. If some domain is empty, then you have no solution. In Bulatov's case, one of the base cases was when diffuser powers algorithm from the previous slide is applicable. So if you have this case, then you just apply the algorithm and get the answer. And in Zhuk's case, it was systems of linear equations over ZP. So of course, the key part of both results is the description of those data reduction rules, how you can reduce your instance, how you can split your instance, and the proof that these rules always reduce in polynomial time to one of the base cases. So this is roughly how the algorithms work. Well, so again, goal reached, conjecture confirmed, and in fact, we mentioned in very many papers that this is the main motivation of this whole direction of research. So this is the ultimate goal, and somehow we made the impression that this is our only goal. So we achieve that, and that's it. We can all retire. But somehow, even in the process, when somehow the community was approaching the resolution of this conjecture, a different motivation started playing a more and more important role. And this motivation is this. So we don't just want to say, here are the tractable problems, here are the NP-complete problems. We want to know exactly why these problems are tractable and NP-complete. We want to know the structure. So in general, I think this is one of the general goals of theoretical computer science, to understand what is the inherent mathematical structure in tractable problems. So these tractable problems, they are polynomial time solvable because they have some intrinsic mathematical structure. What is this structure? Can we somehow explain it in some very general way? So this was a very strong driving force behind this direction. And from this point of view, of course, this result is very significant. It's one of the most significant results, deservedly, but we want to know more. We want to know the same, the reason behind tractability for other problems, not just CSPs, or maybe more general CSPs. So essentially, we know very little about the structure of efficient computation, the mathematical structure of it, and we want to know more. So that's the dominant motivation for this line of research now. So as we were approaching, as a community, the resolution of the Feder-Vardi conjecture, some other problem was somehow lurking in the background and making some noises. And that's the approximate graph coloring problem. So the classical fact is that if you are given a k-colorable graph, then it's NP hard to find a k-coloring for it. So this follows trivially, of course, right? You just run. So if you assume that this task is polynomial time solvable, then you just run your algorithm on whatever input graph you get, and you check the answer. If the answer is a k-coloring, then your graph is k-colorable. If your answer is something else, then your assumption about k colorability was false, and your graph is not k colorable. So that was pretty easy, and that was known for ages since the early 70s probably. So the natural question is this: okay, so you cannot find the k coloring. Now, how many colors do you need to efficiently find the coloring? And here's the state of the art for 3 colorable graphs. So here, these are the best known results. So the positive result is this. We need roughly n to the power 1/5 colors, where n is the number of vertices in the graph. So it's not even a constant, it's some function, some polynomial function in the number of vertices. That's the best positive result that we have by Kawarabayashi and Torov. The best negative result that we have is that finding a 5 coloring for a 3 colorable graph is NP hard. So the state of the art was that finding a 3 coloring was NP hard. That was from the 70s until roughly 2000, when it was improved to a 4 coloring by Kalai, Safra, and Lineal. And then, so 15 or 20 years later, it was improved to 5 by Barto, Bulin, myself, and Opershal. So you can see the gap between the negative and the positive results that we have. And this is not a random problem, right? This is a graph coloring problem. This is something that we as a community studied for ages. And what this shows is that we do not understand the mathematical structure of this problem. We just don't understand it at all, right? Because we have such a huge gap. Right. So it was suggested, I think, even by Gary and Johnson in the 70s, that this is NP hard. Given a k colorable graph, finding a c coloring for it is NP hard for any constancy. This problem is largely open. Actually, this was shown to be true under some assumptions, which are not like unique, well, which are like unique games conjecture, but not quite. Some variation of unique games conjecture. And state of the art is this. So coloring, C coloring a k colorable graph is NP hard if C is 2k minus 1. That's again from the same BBKO paper. And this Kaus paper by myself, Opershal, Vrochna, and Jeavons proved the same result for this number C. So for very small numbers k, such as 3 and 4, this is better. For I think for 5, they give the same number. For starting from 6, the second one is much better. Gives a much stronger result. Okay, now motivated by this, Austrian Guruswamy and Hostad studied this promise problem. So this approximate graph coloring is a promise problem, right? Your promise that your graph is k colorable, do something with it. A promise version of satisfiability was considered by Austrian Guruswamy and Hostad, and it was called 2 plus epsilon sat. So you just define G k sat with 2 parameters as follows. You have an instance of k sat, and you have a promise that there is an assignment. You don't have it, but there is one that satisfies at least G literals in each clause. Okay, so if G is 2, then you are guaranteed to have an assignment that satisfies not just one, but at least 2 literals in every clause. And the goal is to find some normal satisfying assignment. So what they proved is that this problem is polynomial time solvable if k over g is at most 2. In this case, you can use a randomized 2-sat algorithm for Padimetriou, or use an LP relaxation to get a de-randomization, not a randomized algorithm. And as long as k over g goes over 2, the problem becomes NP hard, and hence 2 plus epsilon sat. So these are clearly problems of the same type, and both are 2 plus epsilon sat and approximate graph coloring. Both are CSPs. So one can define a promise CSP problem as follows. So you have 2 structures, A and B, and basically a solution in A guarantees you a solution in B. So then the problem is defined like this. So you have two cases. You have your instance, either it's satisfiable in A or not satisfiable even in B. So on the picture, it looks like this. It's a promise problem, so you have something in the middle that you don't care about. And you need to distinguish between the two cases. That's the decision version. You can also look at the search version. When you are given an instance and you know it has a solution in A, you need to find a solution in B. So there is a reduction from decision to search, but the other direction is open. And this problem, PCSP for A and B, is a generalization of CSP of A, because if A and B are equal, then what you get is just CSP of A. So it's a vast generalization. And if one of these two problems, CSP of A or CSP of B, solvable polynomial time, then you can, of course, solve this or that, and hence the whole PCSP is solvable polynomial time. So this problem is interesting when both CSP of A and CSP of B are NP-hard problems. So and then we have a new goal to classify all those. So let me tell you briefly what happens in the Boolean case. So if we look at 1 and 3 SAT and not all equal SAT, which are the well-known NP-hard problems, then the corresponding PCSP is actually solvable in polynomial time. If I give you an instance of 1 and 3 SAT, and I can guarantee that it has a satisfying assignment, then it's NP-hard to find such an assignment, but you can find in polynomial time a not all equal satisfying assignment for your instance. And here's the algorithm. You replace every 1 and 3 constraint by a linear equation, x plus y plus z equals 1. That's, of course, a relaxation. You solve the obtained linear system over z, which you can do in polynomial time. And then you round your solution for the system. So you map all positive things to 1, all non-positive things to 0. So if your system was, so if your 1 in 3 instance was satisfiable, then of course this would still be a satisfying a solution for the linear system. And then of course, if you look at your equation, then you can see that in this solution to your linear system, you cannot have all x, y, and z positive or all of them non-positive, right? You cannot have that all these x, y, and z are positive because the sum must equal to 1. And if they're all non-positive, then the sum cannot equal to 1 either. Which means that this rounding gives you a solution to the not all equal set. And actually, there are some dichotomies now for Boolean CSPs with symmetric relations only, not general dichotomy. So let me just tell you that this theory of gadget reductions has been extended from CSPs to PCSPs and applied successfully. I need to wrap up, of course. So let me just fast forward and tell you that for promise graph homomorphisms, so I told you that for Boolean CSPs, we know some dichotomies, but there are many cases that are open. You can have a promise version of H coloring. And again, something is known about this version, but there are many, many open questions. So the natural question is there a dichotomy for PCSPs like the one for CSPs? I think it's too early to predict. So what we know is that PCSPs is all about symmetries. It's all about abstract properties of polymorphisms. The difference is that this time polymorphisms act from one set to another set. So you cannot even compose them, which implies that even though the general theory of reductions works, structural universal algebra is not applicable. So you need to do something else. For CSPs, we have this very convenient property that either you have trivial symmetries or very strong symmetries. What you have for PCSPs is that you can have limited non-trivial symmetries, which would give you hardness. Or you can have strong enough symmetries that give you an efficient algorithm. So, but the question is there a gap between limited, non-trivial, and strong enough? We don't know. That's an open question. This is something to work on. And of course, we need more evidence to even conjecture this dichotomy. So for example, classification for all Boolean PCSPs generalizing Schaefer, or classification for promised graph homomorphism generalizing Helm-Nechetriel would be good. Now, of course, sorry, classification for promised graph homomorphisms involves resolving this approximate graph coloring conjecture, right? Which top people in approximation tried to resolve for 40 years and couldn't. So it's not going to be a pushover, right? It needs some new ideas, and I believe we do have new ideas. So let me summarize. This promised CSP is a vast generalization of finite domain CSP, and it includes some famous open problems as special cases. So we have an extended abstract theory of gadget reductions for it, and we have somehow a fresh, broader view on things. We have new algorithms, which are somehow infinite. Like both algorithms of Bulatov and Zhuk, they're very finite. They operate with finite objects. For PCSPs, we have cases where provably we need infinite algorithms, such as involving relaxations, linear programming relaxations, affine integer relaxations, and such like, to solve finite problems. So we must use infinite algorithms. We have new connections. For example, this connection with topology that we use to resolve some cases of promised graph homomorphism. So this is all very interesting. And then we can use this fresh, broader view to look back on the existing CSP results, such as the resolution of dichotomy results. The resolution of dichotomy conjecture, which is currently not accessible to almost everybody. So can we somehow use infinite ideas to provide a different algorithm that will be more accessible, or maybe even explain the nature of tractability better? Looking forward, we can try and explain the general mathematical structure of tractable PCSPs, some general properties that explain it on some very general level. And looking even more forward, we can look beyond CSPs and the family and use this idea of high-dimensional symmetries of solution spaces to provide general uniform explanations of tractability in some wider families of problems. So there's a question in the chat to explain relation to topology. So maybe let me finish, and then I'll explain it. So to wrap up, this complexity quest for PCSPs, it's big, important, and wide open. And I asked this question in the beginning of my talk, are we there yet? And I believe the answer looks more or less like this. We conquered a mountain, but we found a range of even higher and more interesting mountains. So this is where we are at the moment.
Thank you very much. That was a really great talk, taking us all the way from the very beginnings up to the modern times. So appreciate that. And I'll clap for everybody here as usual. We had a question, as you noted already, from Oliver Coleman in the chat window.
Yes, so the relation to topology is like this. So you want to analyze your polymorphisms, say from an odd cycle to another odd cycle, say C3. So your polymorphism is a function of many variables. And somehow you want to derive that only few of the coordinates in your function are really important, and all the rest is kind of noise. So what you have is a discrete function, but then you can make every graph into a topological space, as is a standard procedure in topological combinatorics that was originated by Lowas in the 70s. And then every polymorphism becomes a continuous map. So if you have a direct product of a few odd cycles, so every odd cycle, of course, becomes just a circle. A direct product of odd cycles becomes an n-torus. And then what you want to analyze is a mapping from your n-torus to a circle. And you can do that by using a topological means. And then from that, you somehow derive some information about your original polymorphism, which is just a map from a power of an odd cycle to a triangle. This is how it goes, roughly. Do you have some names of people working on the topology link? Yes, my name. So this link is brand new. It was brought out in a paper by myself, Oprashal, Vrokna, and Jeavons, and it's a brand new paper from last year.
Let's see, I have a question while waiting for other people to come up with theirs. So on the algebraic CSP dichotomy, you mentioned the Bulatov-Zhuk result. In the positive case where there are things R and P, what is the complexity of these problems? Is it similar to, say, SAT, or where
it's
the algorithms
crazy,
are like linear time or something very simple, or do you get complex algorithms?
Well, I'm not even entirely sure that there was a strong attempt to somehow bring this complexity to some reasonable level. I think the algorithms as they are have very, very high polynomial complexity. Okay. It's nothing like you want to see.
Is there any reason to suspect that's inherent, or
I'm not so sure. That's because they work with the somehow with the structure of the problem, the algebraic structure of the problem. And maybe there are some very different approaches, very different algorithms that just don't do this. For example, the algorithms that I somehow alluded to, that are based on relaxations to infinite sets, like LP and maybe some LP hierarchy, maybe a fine integer relaxation, something like this. Mm-hmm. So I'm not sure whether this is inherent or it's just a feature of the approach. And I'm pretty sure they didn't try to reduce this complexity. They just wanted to get it done.
Okay. Good, thank you.
I have a question.
Yes, Albert.
Hi, Andrei. So the question is, in these reductions where you prove the hardness of 2k minus 1 coloring k-colorable graphs, the reduction what is the dependence on k, the running time of the reduction? Is the k going in the exponent, or is it polynomial in n and k?
Oh, well, I would need to think about this. I'm not sure we want to make everybody wait.
Okay, but the reason I ask this is because I wonder whether the difficulty is that growing k's are making the problem. So, for example, could it be that by allowing sub-exponential algorithms, you can do better than this very back gap of n to the 1/5? You see?
Yeah, that's a possibility, of course. Yeah, okay. That's a possibility.
Thanks.
Okay.
Sam, may I ask a question?
Yes, please go ahead.
Andrei, thank you very much for this beautiful and informative talk, first of all. I was a bit surprised at the end. You seem to be negative about universal algebra helping you with the premise problems. It sounds to me more like universal algebra as we know it, or as you know it because you know so much more about it. Why can't you think of extensions of or modifications or generalizations of universal algebra that will allow you to manipulate the symmetries? Does it make sense?
Yes, of course. Yeah, thank you, Fokion. Well, basically the answer is this. In the ordinary CSP, you have functions defined on the same domain, so you can compose them, and this gives you a lot of power. So you can start with some small polymorphisms and compose them in tricky ways and obtain something very useful. And that's somehow this is very important for universal algebra. Being able to to do that. Somehow, if you cannot do this, actually, I discussed this with a few universal algebraists, and I was somehow trying to suggest the same, that it seems it may be not completely irrelevant, And basically, they thought this was heresy, right? If you cannot compose functions, there is no universal algebra.
Okay.
Something is applicable to some extent, but not the structural stuff.
All right. Thank you.
Like we do have this theory of gadget reductions that still works, and that's still pretty algebraic.
So maybe your
structural theories.
maybe your topology is the answer, the substitute to that. I mean, yeah. Okay. Thank you.
Okay.
Good. Any other questions? Yes, there's a question in the window from Antonina. Do you think there's a dichotomy between CSPs in P and NL, like in Schaefer's theorem?
That's a good question. Yeah, thank you. Actually, this is something that's not completely resolved about CSPs. So even a characterization in NL, it's so that there are some negative results and some positive results, and there is a tiny gap between them for NL, which is still not closed. And description of CSPs in NL would automatically imply a description of CSPs in L by result of Kasdan. So I'm not sure about the dichotomy as in Schaefer's theorem, actually, because there is also this case of systems of linear equations, which of course have their own complexity class. And it's not clear. It's not clear how this complexity class relates to NL. So you can have some kind of not dichotomy, but tetrachotomy, whatever chotomy. But it will still have some uncertainty because we don't know how solving linear equations relates to NL. This is open. So something can be done, but we would have more cases.
Mm-hmm.
So hopefully this answers the question. Okay.
All right. Oh, another question. Thomas Koch has a comment. Question.
So stricter CSPs could be represented by a more coarse topology. Well, it's a very general remark. I cannot say that this is the main idea. I wouldn't be able to put the main idea in one line like that.
Okay.
I think that the main idea is that topology somehow represents the homomorphism better because you have if you have like K coloring, then you have many colorings, say 10 colorings of K4, and you can move between them, and this movement somehow corresponds to what you can do with continuous transformations. So somehow topology reflects the fact that you can switch between different homomorphisms from A to B. You can transform one into another, say via recoloring. And this recoloring is a somehow topological process. I don't know if this makes much sense.
So does this mean that the connectivity of the solution space is relevant?
Maybe not necessarily connectivity, but some other topological properties. Or maybe, in topology, there are many connectivities on different levels.
Interesting.
So what is a homeomorphism then? Regarding this on the topological side, can you say algebraic homomorphism can be transformed into homeomorphism maybe? Oh. Just an idea.
Well, again, I'm not so sure. Sorry.
Okay, well, if there's no other questions or comments, I guess we'll wrap things up. Thank you again for the very thorough talk, very nice. And thank you everyone for attending, and we'll see you guys here next week. And there's a fellows talk in about 15, 20 minutes as well. If you're interested in that, you might check it out. So thank you again.
Thank you.
Thank you.